Let's determine if this series converges or diverges. We see that we have an alternating series, and so let's see if we meet the conditions for the alternating series test. First of all, we would need this to be positive for our n going from 1 to infinity, and we can see that we do have that condition. Next, we would need these terms to be decreasing. Well, let's look at a function that has these for its integer terms, and let's take a derivative and see what we find. If we can show that it's always negative, then we would know that it's decreasing. So let's take a derivative. This is going to be quotient rule, bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, so that's going to be a 1/2, and then x cubed plus 1 to the minus 1/2, and then we've also got the chain rule. I'm just going to have to squish it on after here. This is also multiplied by 3x squared, and then all that is over the bottom squared, which is x cubed plus 1. Okay, so let's go ahead and rewrite this so we can read it and then simplify it. So combining things here, it looks like we have minus 3/2 x cubed, and that's over the square root of x cubed plus 1, and then that's over x cubed plus 1. Now we can multiply numerator and denominator by the square root of x cubed plus 1, square root of x cubed plus 1. And what that does when we do that here is that will leave us an x cubed plus 1, and then it'll cancel this and leave us minus 3/2 x cubed, and in the denominator these can combine to give us x cubed plus 1 to the 3/2. Okay, and finally we can combine our x cubed terms, so we have 2/2 minus 3/2, so minus 1/2 x cubed plus 1 for the numerator, and then x cubed plus 1 to the 3/2 for the denominator. Now, as we look at this, remember that our domain was from 1 to infinity, so this is always going to be positive, and if we put a 1 in here, we would get a positive term, so the function would not be decreasing. But if we put in anything greater than 1, if we have a 2, a 3, and so forth, this term is going to be larger than 1, and so our derivative will be negative. So this does decrease after the first term, so we could express the first term, which is a finite, and then we could look at the series from 2 on, and it is decreasing, and look at the convergence of that, and then adding a finite term won't change the convergence. So we have it decreasing for n greater than or equal to 2. And then our last thing we need to check is we need to look at the limit as n goes to infinity of these terms. And while I do that, I'm going to multiply numerator and denominator by 1 over n. So that will make the numerator 1. The denominator, if I multiplied it by 1 over n, I could write it as n squared square rooted so that I could bring it underneath the square root. And that would give me n plus 1 over n squared underneath the square root. Now I'm going to let n go to infinity. This will go to 0. Numerator is fixed. Denominator is going to become larger and larger, and so in fact we do meet our third condition of the limit of the terms as n goes to infinity is 0. So we've met all of our terms for alternating series, and therefore this series converges by the alternating series test.